All right, when our transistors are operating, we typically try and do what's called bias them. So we establish a bias point, or sometimes a Q point or quiescent point. And what we're going to do here is we're going to set the voltage and current to be a specific DC value, and this will dictate the performance of the transistor. Now, before we get there, we should note the current flows in normal forward active operation for an NPN. We have our base current going into the base, we have our emitter current coming out of the emitter, and our collector current going in the direction of the emitter current from the collector. In a PNP, it's the opposite. We have the emitter current coming down into the emitter, the base current exiting from the base. The collector current continuing on in that direction. Now, in either case, we can use KCL to say that the emitter current is equal to the sum of the base current plus the collector current. All right, so now if we start with a transistor and we sweep the collector to emitter voltage and the base to emitter voltage, or maybe several different base to emitter voltages, we'll get a set of curves that look like the ones that are depicted here. So for each VBE or VEB, if we're using a PNP, we would see a curve that looks something like this. We'd start off at 0. Over here, this is our cutoff point. And as we increased VCE, we would see the current start to rise kind of exponentially, and then ultimately it would flatten out and ideally become flat and independent of the collector to emitter voltage. Now, the voltage at which the current becomes independent is sometimes called the saturation voltage. We normally label this as VCE sat, and it's typically approximately equal to 0.2 volts. If VCE is greater than VCE sat, we're in the forward active region, and if it's less than VCE sat and the transistor is on, we're in the saturation region. Now remember, for the most part, we're going to try and operate in the forward active region. We're going to do so by setting a Q point or a bias point. And our Q point is some specific combination of collector to emitter voltage, call it VCE Q. This would be for an NPN. If we were looking at a PNP, we might label it VECQ. And for that particular combination of VCE, VBE, there will be a collector current, or ICQ. Now, as I said, we usually label this our Q point or quiescent point, or sometimes our bias point. Now, the bias or Q point is the DC voltage and current around which there will be small signal voltage and current swings. So when we're using these appropriately, we're going to set a DC value, and then we're going to put little wiggles or sinusoids around that value, and the transistor will ideally serve as an amplifier. To find our Q point, we have a procedure. The first thing to do is we assume forward active region. Next, we're going to use KVL, or Kirchhoff's voltage law, around the emitter base junction. And we're going to find the collector current. And remember, we're going to do this because the collector current was defined as IS times e to the VBE over VT. So the collector current is dependent upon the base to emitter voltage. After that, we're going to use KVL around the collector to base junction. We're going to check if VCE is greater than VCE sat, which remember was approximately 0.2 volts. And if it is, we assume that our assumption of forward active region is correct and our bias point can now be calculated. If not, we have to rebias the device. If we were using a PNP, we would simply say that the VEC has to be greater than VEC SAT. Again, typically VEC SAT is around 0.2 volts. All right, so with that, we'll start and try and find a small signal model based upon this Q point.